Okay, so welcome to the second lecture in the Discrete Math for Algorithm and Software Design course. Let me briefly recall what happened last week. So we discussed Boolean formulae. Okay, I hope we can.
Нужно синий. А если нет, синий. Сейчас может
Okay, so we'll try to get a better writing device. So now I'll just speak. Okay, so we discussed Boolean formulae, and we discussed the question of satisfiability for them. So satisfiability means that we don't wish the formula to be always true, but we wish the formula to be true sometimes. So there exist such assignments of Boolean values, this means zeros and ones, to the formal variables of the formula, so that the formula becomes true. So this is basically this section of our of the things we're going to discuss during the first part of the course. And we considered a specific sort of Boolean formula, which is called conjunction normal form, CNF. And a formula is in CNF if it is a big conjunction of disjunctions. And each elementary disjunction consists of literals. Literals meaning variables or their negations. So there's either variable or its negation. For CNFs, so there is also a dual notion of DNF, which is the disjunctive normal form. And for DNF, the satisfiability question is actually trivial, because the DNF is a big disjunction, or a big disjunctive symbol, of some clauses, conjunctions. So to satisfy a disjunction, one has just to satisfy at least one clause. So if we satisfy one clause, we satisfy the whole disjunction. So then we just try each clause one by one, and each clause of the. Oh, thank you. Okay, so in the DNF, you have a big disjunction, so there is clause 1, disjunction, etc., disjunction clause n. And in the DNF, each clause is a conjunction. So C1 is literal 1, 1, conjunction literal 1k. And satisfying this just means that it doesn't have a contradiction. So to satisfy a conjunction, one just has to check that it doesn't include P and not P. And then one just checks this. So this is a fast, efficient algorithm for checking satisfiability of DNF. So we will call this problem DNF sat. So this is easily doable on a computer. So another question is CNF sat. Or this is actually usually denoted by just SAT, satisfiability problem, because this is interesting. This is a hard one. So what's really going on? This is the satisfiability problem for conjunctive normal form. And how can one do it? Well, we discussed the method which was called resolution method. And now we'll prove the theorem that this method really does the job. So what does resolution mean? So the CNF is a set of clauses, conjunction of clauses. Each clause is a disjunction. So it's going to be, our CNF is going to be C1, well, we can say, yeah, D1. Disjunction dm, and each disjunction di is literal I1, No, here should be conjunctions, of course. And here should be disjunctions. Literal I, Ki. And because conjunction is associative and commutative and highly we can just look at this as a set of clauses, a set of elementary disjunctions. So we can write stuff like this, just D1, comma, Dn. So the order doesn't matter. If we have two copies of the same, we can just make it one. Everything doesn't. Okay, and now we're going to apply the resolution rule. So the resolution rule, I just recall it, it's something like that. We have one disjunction, which is A disjunction P. So this just means that this is the clause which includes P. A could be empty. So it could be just P. Or it could include something else. So material. And also we have not P, we'll write it like this, P with the bar, disjunction P. And we can just, now we can resolve. So this is the resolution rule. And it says that A or B. So by the way, just as a matter of fact, we know that implication is also disjunction. So say P implies Q is the same as not P or Q, right? So this means that if we write down not P or Q here, and then we write P, then we'll get Q. It's just a particular case of resolution rule. And this can be rewritten in the following form as P implies Q and P, this yields Q. This is the famous rule, which is called modus ponens. The standard rule of classical logic, that if you have an implication and you know its right-hand side, you can derive its, if you know its left-hand side, you can derive its right-hand side. So it's the rule of, standard rule of inference in classical logic. And resolution is in a sense a generalization of that. So this says that P implies B. This is just the same because not P or P. And here you say either you have A, then you just use it. Or you have P, and then you can imply B. And therefore you have A or B. So what is the status of this rule? So we're looking for satisfiability. When we look for satisfiability, we take our, actually we're trying to falsify our CNF. When we try to falsify it, we try to obtain contradiction. So we take the CNF, it is a set of clauses, so it's conjunction, so we suppose that all of them are true under some specific assignment. We don't know this assignment, but we think that this is true. And then we, what we do next, we try to infer some other clauses which logically follow from these ones, using this rule. So this rule says that if this is true and this is true, this should also be true. And we try to obtain a contradiction. So the empty clause is a contradiction, because how can we get the empty clause? By resolution. We can get it only this way. Yeah? And this is exactly contradiction. It's P and not P. So what are we going to do? We start with our big CNF and we apply a resolution, and if we obtain the empty one, we get false. We get that this CNF is not satisfiable. But the question is, when it is really satisfiable, what happens? So the trick is that the total number of possible clauses in a CNF is limited. Because we did this calculation last time, I will repeat that each variable can either appear positively or appear negatively or not appear in a concrete clause. Therefore, the maximal possible number of clauses is bounded by 3 to the power of, well, not n, well, let's put m here. It's convenient to use m, n is the number of variables, and m is going to be the number of clauses. So m is always less or equal than 3 to the power of n. So therefore, if we apply resolutions and we do not obtain empty, at some point, we stop getting new clauses. All the clauses are either already there or cannot be obtained by resolution from the original CNF. This situation is called the saturated situation. So saturation means that we cannot obtain new.
All the variables on the right place is the equality.
Yeah, the number of clauses.
It's the number of variables.
No, M is the number of clauses. N is the number of variables. So N is the number of variables. N variables. M clauses. So a CNF is called saturated if there is no, say, progressive resolution to apply. So we can apply resolutions, but they will yield clauses which are already in our CNF. So this is how it basically works. Okay, now, yeah, this was really going to happen here. So now we have to prove the theorem which is traditional for logic, which is called completeness theorem. So a CNF is satisfiable if and only if, we write it like this, if, means if and only if, its saturation under resolutions does not include the empty clause. So there are two directions here. So if the CNF, so okay, if the CNF is satisfiable, so this direction, this is the easy one. This is easy. If the CNF is satisfiable, then you have a satisfying assignment. Under this satisfying assignment, all clauses in the CNF are true. Therefore, if we saturate it, then the new clauses which we add using resolution, they will also be satisfied, they will be true. This empty clause is always false. This means that it cannot appear when we saturate, when we apply resolution. So this is the easy direction. This is called soundness or correctness. The hard one is the opposite one. So suppose we did the saturation process and we did not obtain false. And what happens then? Why we really get satisfiability? So we have to obtain a satisfying assignment from that. And this requires a bit of work. So let us first, let's start with just a bit to start with. How can we obtain the things? So we proceed by induction on the number of variables. So induction means that we how to say this? We can start with an easier case where we have only one variable, and then from the case of n variables, we move to the case of n plus 1 variables. And gradually we cover all the possible cases. So we start by induction on the number of variables and start with the number of variables 1. We actually could do it with 0, but this would trivialize things because what can you do with 0 variables? Come on, there are only 2 possible. So let's say n equals 1. Okay, so what are the possible clauses with n equals 1? How do you think? How many of them? 3. So we have P. Let's call the variable P. We have not P. Also, we have the empty clause. So if say we have both P and not P, then we will obtain the empty clause by resolution. Or it could be available in the original CNF. Okay, so these are all possible clauses, no more. Now we suppose, so we go this way. So the saturation does not include the empty clause. What does that mean? It means that there could not be both P and not P there. So if we have this, we already fail, because even before saturation we have the empty clause. If we have both of these, we also fail because resolution gives this. So the only case where there are 2 cases when we do not get empty, it's either when we have P and not this one, and either or we have this. So this is either we have P or we have not, as the only clause in this here. In both cases, we are fine, because the third possible case, if the whole CNF is empty, we don't have any clauses. The empty conjunction is true, and it's satisfied by any assignment. If we have only this, it is satisfied with P equals 1. And this is satisfied with P equals 0. So both of these guys give satisfiability. Okay. So next we have to proceed by induction from n to n plus 1. So suppose our statement is already valid for n, and we try to add an extra variable. So, and our variables are going to be P1, Pn, and let the n plus first variable be Q. This is the extra variable we're trying to add. And now, let S be our CNF. So S is a set of clauses which include P1, Pn, and also Q. And now we do the following thing. We consider 2 different CNFs. So suppose we have S, we will take S plus, and we'll take S minus. So what is S plus? S plus is the CNF. So we take the clauses from S. So let me write this down. This is the crucial part. So S plus is the set of all clauses of S without not Q, and with Q removed. So intuitively, what's going to happen? Yeah, they say that people should turn off their microphones. It's not for me. Yeah. So what intuitively what we're going to do here? We say that we try to consider that Q is true. We'll actually do a sort of case analysis here. If Q is true, then we do not want the clauses of S which conflict with Q, which say that Q is false. So we just remove them. And then if a clause contains Q, we just say we'll remove it because we consider it true. So this is a Q positive part of S. And this is the set of clauses of S without Q and with the dual removed. So this is how it works. There are 2 new CNFs. So how many variables are there in each of these CNFs? How do you think? And well, maybe less. There could be, so it's, for example, this could not include some other variable, but the number of variables here and here is less or equal to n. We removed q. We have only these variables. So we can apply induction. We can apply our theorem for this direction interesting to each of these guys. And what are we going to get? So we claim that, well, we proceed by, so what we're going to do, we suppose that our saturation does not include false, and we suppose that S is not satisfiable. So we're trying to prove that it's satisfiable. So we say, suppose S is not satisfiable. And we shall prove that in this case, both of these guys are also not satisfiable. So how do we proceed? So S is not satisfiable. So suppose that S plus is satisfiable. If S plus is satisfiable, what does this mean? There exists a satisfying assignment. So alpha by assignment alpha. Well, what we're going to do? So what we are saying, we say that we want to prove that S is satisfiable. We suppose that it is not. And then we claim that these two are also not satisfiable. So if S plus is satisfiable, what's going to happen? So then there is a satisfying assignment for some assignment alpha which satisfies S plus. Okay. Now let us do the following. So let's take alpha does not include Q. So S plus is a satisfying assignment which works only on Q1 Pn. And now let's take alpha on Q, which is going to be 0. So again, suppose that this guy is satisfiable, and we take we take 0 for Q.
What does assignment mean?
Assignment means that it's a function which assigns truth values to variables. So it's a function from variables to zeros and ones. So a satisfying assignment is an assignment which makes the formula true. So we have this S plus. Suppose we manage to satisfy it using some function alpha, which maps these variables P1, Pn to zeros and ones. Then let's take alpha of Q equals 0. If we take it like that, then what happens? S plus is still satisfiable. Therefore, if we take the clauses of S, the original S, then, well, we could add Q's, but these Q's will be added by disjunction. So we have something in S plus which is already satisfied. We add false, but it's false by disjunction, so it doesn't doesn't falsify it. And so how do we take it? So okay, this is S. So here are clauses which include not Q. And here is S plus. Well, it's S plus, but maybe we removed Q from it. Or maybe added Q to S plus. So here we have already satisfied everything, yeah? Because this alpha satisfied S plus. And here we satisfy just by Q equals 0. Because outside S plus we have not Q. So this means the following. If S plus is, so let's put it as just a number. So if S plus is satisfiable, so is S. So this is the crucial point here. It has, say, here we have many dualities, many tricks that we go by contraposition. But let's think about this once more. So we take this. So we take the set of clauses, which so we remove the clauses which are negative for Q. If we manage to satisfy everything else without using Q, just using these P1, Pn, then we can just say that let's take Q to be false and satisfy the remaining part which includes not Q. And of course, there is another point in this lemma that if S minus is satisfiable, then so is also S. Because again, what do we do here? We take all the clauses which do not include Q and manage to satisfy them without using Q. So we satisfy them only using some values for P1, Pn. Our satisfying does not depend on Q.
But doesn't it mean that we just used the mass induction when we propose that n value was satisfiable, and we just say if n satisfiable, then n plus 1 satisfiable.
No, we didn't yet use induction. So we are going to use it now. Because we didn't use the theorem. So the theorem says something about resolution. We just made a conditional statement that if this is satisfiable, then this is satisfiable. Now, what we're going to do next, we're going to apply this lemma for S plus and S minus. Not the lemma, but the induction hypothesis. So what we're going to say now is that if we cannot get false, then we cannot get it in, say, so in S plus or in S minus. So now we're going to use induction. So first, let's again think about this lemma. So this should be clear. So we define this S plus and S minus, and if at least one of it is satisfiable, then so is S. And now we're going to use induction.
Антон, дополнение, что в Theorem она где мы это используем?
Well, we use it here, that if we want to, so we want to satisfy S. So in S, we have clauses without Q bar and clauses with Q bar. If we take a clause with not Q, we satisfy it just by saying that Q is false. But if we have a clause with Q, then if we didn't remove it, we could satisfy it using Q equals true. So for example, suppose we have a trivial CNF which is Q and not Q. Then if we don't remove Q, then we will have S plus, something S plus like this, equals Q, and S minus equals not Q. These are both satisfiable, but this is not. But if we remove Q, then this is just the real S plus. It's going to be empty. And this is also going to be empty. They're both empty. And they're not satisfiable. And this is okay.
Почему делить на S плюсом и S минусом, если мы изначально постулируем, что с P1 по Pn у нас получается оно satisfiable, и нет смысла разбирать по отдельности, если мы так сказали, что без Q оно satisfiable.
Yeah, it's called satisfiable. It's not satisfiable without Q. So if we just take S and just remove all the Q's, then it's not equivalent. So what I'm trying to say, you say that you take S and just remove all the Q's and Q bars, yes? So we know that, yeah, the problem is with this resolution. The problem is that if we add these Q's, we of course we will keep satisfiability. But the question is why we keep this saturation thing. So we have to for Q we have to consider these cases, because this is a random example. It's a very trivial, but it shows everything. Q and not Q. If you remove Q, Or for example, no, this is a dual. Just take a CNF which includes just Q. What's going to happen? If we remove Q, just remove it, we'll get empty close. It will not satisfy them. So what we're going to say now, let me just remove this. So we say the following. So if saturation on S doesn't yield empty, then so does saturation either for S plus or for S minus. So you see that we had this original S. If we just remove the Q's, we can make the CNF stronger. We can make it not satisfiable, and not so. Not yielding. In S, we could not get empty clause using resolution. But if we remove Q's, we could make an empty clause. But using this S plus and S minus, at least in one case, we will get satisfiability. And this corresponds to the idea that either Q is 0 or Q is 1 in our satisfied assignment. So we have to implement the choice for Q. We cannot just remove it, just saying that it is safe, always true. So what means we remove Q? It means that if we just remove the Q's, it means that we consider Q always false. Okay? It doesn't help us to satisfy. If we remove both Q and not Q, we have something strange. What does it mean? So, okay. Let's return to the proof. So, again, we had a CNFS. We considered S plus and S minus, which are two, say, parts of this CNF. And we say that if at least one of these is satisfiable, then S is also satisfiable. So if we satisfy this, we satisfy S. If we satisfy this, we also satisfy S. And this corresponds to the two ideas of satisfying. So either we satisfy it with Q equals 1, or we satisfy it with Q equals 0. Yeah? This is actually the answer. And actually, this is the criteria that S is satisfiable if and only if one of these is satisfiable, maybe both. So this is the thing when we try to satisfy it, it means that we just choose Q. Two possible cases for Q. Okay, now what we're going to do to finish the proof. So suppose saturation yields empty here and yields empty here. So suppose the contrary, suppose that we cannot satisfy S plus and we cannot satisfy S minus. So, okay. How do we say this? So if saturation yields empty here and yields empty here, then we claim that saturation also yields empty here. How do we say this? So we saturate S plus, we saturate S minus, and in both cases we get empty. What does this mean for original S? So what is empty for S plus? It's a clause which is empty, but we removed Q. So in the original CNF, it could be just Q. So again, we have the resolution process, and we apply it to S plus, and suppose we obtained empty. This means that before So before removing Q, we had this Q inside. Because we can say it like this. What is S plus? We took S, we took a subset of S, it is here, and we have hidden the Q's. So we remove the Q's. We have just, let's see, we didn't remove, we just have hidden them. After doing that, we applied resolutions. And applying resolutions, we obtained empty. This means that there could be a hidden Q there. So in S plus, we obtained empty. In the original S, we obtained Q. Yeah? Because the Q's got hidden, they got removed. Usually, if we obtained empty here, then in the original CNFS, we obtained not Q. Because again, it got hidden. Or maybe we just obtained empty if there were no not Q there. But again, so there are two possibilities. If we obtain empty in S plus, then we either obtain empty in the original S, or we obtain Q there. Here, if we obtain empty here, then we either in the original CNF, we either obtain empty, or we obtain not Q. So what happens? If we obtain empty, then in the original CNF, then it's contradiction because we suppose that we could not obtain it. It's our presupposition. So this means that we obtained Q. If we obtained empty here in S, we obtained Q. If we obtained empty here in S, we obtained not Q. But then we have these two resolution processes, one of which gave us Q and the other gave not Q. And then we can apply one more resolution and get empty. So this means that if we obtained empty here and obtained empty here, then we obtain empty in the original CNF. And this means that if we did not obtain empty in the original CNF, then we couldn't obtain it either here or here. But we suppose we didn't obtain empty in this. Here we have n variables. Well, let's recall them. This means that if we didn't obtain empty in S plus, then by induction, here we use induction, S plus is satisfiable by this theorem for n. And if it is satisfiable, then by this lemma, the same happens for S, with Q equals 0. And usually, if we manage to satisfy, so if we didn't obtain empty here, then we satisfy S minus, and using this lemma, we again satisfy S. So actually, this is a criterion. S is satisfiable if either this is satisfiable or this is satisfiable. Well, this or is not exclusive because there's a disjunction, and this disjunction is how to say this can, so yeah, well, it's not exclusive. So this guy means that satisfying this means satisfying the original S with Q equals 0. Satisfying this means satisfying the original S with Q equals 1. This could be both both good possibilities, because S could be satisfiable with either Q or maybe not Q, or maybe with both. So the trivial case is that suppose that S does not include Q. This could happen. Then just this and this will be just S. This is formal induction that we could just say, okay, S doesn't include Q, and we can apply induction for other elements. So this is a proof of completeness. This is a theorem of completeness for resolution method. This reasoning is presented in the lecture notes. You can see it there on the course's webpage. And this thing is the motivation for resolution method of checking satisfiability. So we start with the CNF, we apply resolutions, and by applying resolutions, we get either empty, which means contradiction, and this is not satisfiability. We did this last time. Or we saturate. We apply all possible resolutions and do not get contradiction. And by this theorem, this guarantees that the formula is satisfied. So this is the result of this theorem. Well, this algorithm gives us answer yes or no. It does not give us the actual result, the satisfying assignment. So it's a good question for you to think about. We'll answer that at the end of the talk, at the end of the course, sorry. How to modify this algorithm in order to make it yield the satisfying assignments. So again, what is the question? So resolution method starts from a CNF and gives us the answer whether it is satisfiable or not. So it starts saturating. Either it obtains the empty clause and says that, okay, our formula is not satisfiable, or it says that I have saturated, there are no more possible clauses, I did not find a contradiction, and this means that the formula is satisfiable. But saying that it is satisfiable does not yield a real assignment. Usually in practice, what we have seen in the practical class, usually in practice we say that it's easy to understand what is the satisfying assignment, because when we do resolution, if we do not get empty, we usually get small clauses which include, say, just P or not P, and this imposes a particular satisfying assignment. But sometimes it doesn't happen like that. So a standard example is actually the following. So we start with the standard formula, which is Gödel-Lambert. P implies Q or Q implies P. This is a tautology. Then we say that, let's take its negation is going to be, say, let me do it. So it's P and not Q, P or not Q. No, it's and here, P and not Q. No, this is a bad example. It's going to be not satisfiable. So then let's try something else, which is generally satisfiable, but which has a polar, say in a sense, polar satisfying assignment. So for example, I take P or not Q. No, this is not better. So P or P or not Q, and I don't know, R or not S. So this is just, well, this is CNF. It's satisfiable. And what does resolution say? Resolution says something very trivial. It says there are no possible resolutions to apply. Therefore, it's saturated. It's saturated, it does not include the empty clause. Therefore, it's satisfiable, yeah? But it doesn't say us what is the satisfying assignment. Well, actually, many of them, you can just arbitrarily say that take P and take, I don't know, R, or take P equals 1, S equals 0. So this gives us only the answer yes or no, but does not give us the satisfying assignment. So this sort of algorithmic questions, it's called decision problem. So a decision problem means that you have an input data. Input data is some finite object. It could be a formula, it could be a graph, it could be just a number, it could be a string of symbols or something like that. And the answer is binary. So it's either 0 or 1. So it's yes or no. And the typical decision problem is the problem of satisfiability. And what we're going to discuss next, it is so what we have obtained by now. We have obtained the fact that SAT is decidable, is algorithmically decidable. So we can even formulate as a theorem. So this satisfiability problem, which we denote by SAT, is algorithmically decidable. Well, this was actually obvious even before all these resolution things, because what algorithm, well, the easiest algorithm could be implemented for deciding satisfiability algorithm. Yeah, you can just take the truth table. You can compute the complete truth table and just get the answer. So you just look at the last column and say whether they're all ones or no, all zeros. This means not satisfiable. If there is at least one unit, that is going to be satisfiable. So this theorem is easy, but we want to get something more. We want to think that, so what was the difference? So the algorithm which tries to find out which, for each line in the truth table, whether it is true or false, we understand that this algorithm is vastly inefficient. When we try to apply it, for any input data, it should try actually 2 to the power of n possible valuations for variables, independently from what it is, what the original formula was. So it takes at least this number of operations, and actually more, because for each possible assignment, you have to compute the value of the formula. And we have an understanding that, say, computing the value of the formula for a given assignment, this should be easy. Yeah? This should be, in a sense, fast. And trying to enumerate all the possible assignments, this is exponentially hard. But this includes many operations. And we have to formalize this intuition. So what algorithms are fast, in a sense, tractable, as they say, which require a modest number of operations, and which algorithms are slow. So for resolution, well, unfortunately, the situation is not significantly better, because, okay, we try to saturate, and when we saturate, then what happens? Actually, we possibly could enumerate all the possible clauses. And the number of possible clauses, as we know, is bounded by even 3 to the power of n. So it's, again, in a sense, inefficient. But let's consider the following special case. So let me remove the proof. And let me say the following. So we have the special case, which is called 2CNF. And in the 2CNF, we have the problem which is called 2SAT, which is satisfiability for 2CNF. So in the 2CNF, we have only, at maximum, we have 2 possible literals in each clause. So each clause is either empty, or it is just P, or it is not P, or it is P of U. Well, or maybe, I don't know. well, literal 1 or literal 2. So it could be not a P or not Q, for example. But we're not allowed to have 3 or more literals in the clause. So how many steps does one take to proceed with resolution method for this 2CNF? How do you think? So there are many variables, but in each clause there are only 2 of them. So a typical situation is when we have just some implications of this form. So P implies Q and Q implies not P, for example. So something like that. P implies Q, Q implies not P, and I don't know Q. Is this satisfiable or not? So we have Q, then we have not P. Okay, it looks like it's satisfiable. Q equals 0 and P equals 0 and Q equals 1. So here we can say that this is, of course, this. This is like this. These are the clauses. We apply resolutions and we say that it's going to be not P. And we're done. This is the saturation. So saturation here makes things, it happens fast. Why? Well, the key trick is that what happens if we saturate, if we apply a resolution to 2 clauses in such a CNF? Yeah. So the trick is that if so we have, so in general, resolution works as follows, yeah? But what are A and B here? A and B are at maximum, they are literals. So here are less or equal than 2, including this not B. Here is less or equal than 2. So in A, it's either literal or it's just empty. And B is also either literal or it's empty. Yeah? Therefore, here we also have at maximum, at most, 2 literals. So we can formulate as the following fact that saturation, so okay, yes, a saturation of a 2CNF is also a 2CNF. So then the size of clause does not grow when we apply resolutions to a 2CNF. Yeah. So this is a principal difference from 3CNF. So if we allow 3 variables or 3 literals, we can do something like this. Q or R or not P, S, P or S or say not T, I don't know. We apply a resolution, and what we're going to get? We're going to get Q or R or S or not T. So you see, if we have at least 3 literals in a clause, then applying resolutions will grow the clause. It will become bigger. And we can get exponentially many clauses when we apply resolutions. But in the 2CNF, applying resolution does not yield bigger clauses. And now we have to do a bit of combinatorics. So suppose that we have n variables and we have a 2CNF. How many clauses, maximum possible number there could be? Yeah, so each one can be included in, yeah, so 2, yeah, no, I think it's, yeah, it will be an estimation, of course. So I would say that it's going to be the binomial coefficient that, no, it's much less, it's polynomial. Come on. So we have two clauses. So this means that each literal, so we have clauses of two literals. Each literal is either a variable or its negation. So we take the choice of from 2n of 2. Or some of you in which use this Russian notation, they write it like this. Oh, yeah. Do you know this stuff? Phenomenal coefficient. Yeah. So this is unfortunately this is not all, because also you can have just clauses with only one literal. So this number of clauses will be at maximum 2n, yeah? And also, potentially, you could have the empty clause, which is a contradiction. So this is plus 1. And this is the estimation for n. This is a bit rough, because we also included unnecessary clauses like this. So we can have P or not P. Such a clause is included here, because P is a literal, not P is also a literal. It's different from P. This clause can be always removed because it's also always true. That doesn't mean anything. But we included it here actually for a good reason, because when we apply saturation, when we apply resolution, we couldn't get this. We could immediately remove this, but in practice it appears. Okay, and let's just compute it. So what is this binomial coefficient? It is 2n multiplied by 2n minus 1 divided by 2 plus 2n plus 1. And this is going to be, well, let's compute. So here we can just cancel this 2. We have 2n squared. Then what about this? It's going to be minus n here and 2n here. So it's plus n plus 1. So this is the maximum possible number of clauses which could be obtained by applying resolution to a set. Yeah. Great. So now, well, we have to be a bit more accurate in computing the efficiency of this algorithm, because we have to implement something like, I don't know, search for the correct for the pair of clauses for which we could apply resolution and stuff like that. But we have this idea that the whole computation, its running time or the number of operations we perform, will be bounded by a polynomial of the input size. So, for example, the polynomial of n, where n is the number of variables, and the input size is something like not bigger than n squared. So it's super polynomial. So this means that we get this result that true set is decidable in polynomial time. So why are we talking about polynomiality? We could make a better statement. We could say that the number of clauses is square. Well, even in the worst situation, the number of, even if we implement it really in a barbarous way, we could do something like a cube, I think, or maybe n to the 4. So we can do a concrete complexity estimation. But in the general theory of computational complexity, the notion of polynomiality appears to be much more robust than the notion of, say, quadratic time or something like that. Because the notion of polynomiality, first, it's independent from any most details of the implementation. I didn't discuss now how do we really implement the saturation process. How do we organize our clauses in the memory? How do we perform some forward-backward search around them? all this stuff is details of the implementation, and this does not affect polynomiality. While it can affect the form of the concrete polynomial. It could be, say, when we try to implement it, we could get cubic, we could get biquadratic time, depending on how clever we are in implementing that. The second thing, which is theoretically more important, that polynomiality does not depend on the computational model we are using. So, of course, in theoretical computer science, we have to use a theoretical model of a computer. So, the real computer is a real physical object. Actually, it is finite. So, you cannot do computations with arbitrarily large natural numbers actually there, because the whole memory is finite. Even if you implement, say, I don't know, long natural or something like that, or integers, you will still have a limitation. But on the other side, for theoretical considerations, it's more interesting to use asymptotical behavior of the computational complex. So we're interested in how our runtime grows when the size of input goes to infinity. So we have to use a theoretical model of computation. And there are many such models. We'll discuss some of them in this course, like Turing machines, like Minsky machines, like random access memory machines, which come closer to real actual computers. So so they're all mutually equivalent. This is called the Turing Church thesis. But if you have a Turing computational model, it's equivalent to Turing machines, equivalent to any possible ideal computer in the world. But if you do these translations, really, then the running time could change. Even if we take, say, a Turing machine with 1 tape and Turing machine with 2 tapes, then there is a quadratic difference. But polynomiality still keeps. So if an algorithm is polynomial for Turing machines, it's also polynomial for any other computational model, and vice versa. This is the reason why people use this idealistic notion of polynomial time computation instead of doing something more concrete, saying we want quadratic or we want 10 log n. So, and this makes these theoretical considerations easy. Of course, when we do implementation, we have to be more accurate and see what's the real, say, computation time, because if we have a very big degree of polynomial, then actually this algorithm is untractable. This is, by the way, one well-known example of that, a decision problem of prime numbers. So we have a number which we want to check whether it is prime. It's quite an important thing, say, in cryptography and stuff like that. And the primality tests, well, they usually were probabilistic. The deterministic tests, they were exponential in time. Well, exponential means that it's exponential not on the number itself, but on its logarithm, because if you input an actual number, then your input size is well, roughly speaking, the logarithm of the number of digits, binary decimal digits. And the standard, well, known since ancient Greek mathematicians, the standard algorithms for checking primality, these algorithms were exponential. There were probabilistic tests which are still used, and at some point it was in early zeros, 2006 or something like that. There were 3 guys, I think from India, who invented a polynomial, deterministic polynomial primality check algorithm, independent from any conjectures or something like that. But this algorithm had some complexity like n to the power of 11. So theoretical question was solved, but for practice was meaningless. So such examples exist, but usually if the problem is polynomial, then there exists a good, say, practically tractable algorithm, so not more than cubic time. So now what we also have, and this is, I will end this lecture by this. So we also have the DNF set is also decidable in polynomial time. Now what about 3 set? So for 3 set, resolution doesn't give us anything good. And the question is, does there exist a good algorithm? So now the only thing we have is some sort of just brute force search. Either we brute force the truth table, or we brute force the saturation in resolution process, which basically gives the same exponential time. Well, even resolution may perform worse. So the real, this is the question, and the answer is, well, we don't know. But it's highly likely that the answer is negative. And for this, there was invented a substitute for this negative answer, which is called the Theory of Np-Completeness, which we're going to discuss in this course. And we shall prove this famous Cook-Levin theorem, which says that SAT and 3 SAT are NP-hard. That means that, well, if some well-known conjecture is true, then there's no polynomial algorithm for this. So then this is the difference between true SAT and 3 SAT, or DNF SAT and CNF SAT. Of course, you can translate your DNF into CNF or CNF into DNF and apply DNF SAT, but this translation is not polynomial. So you will lose your polynomiality at this time. Decidability is still there. So I think I ran out of my time, but we started a bit later, so I will just say some final words now. So today we discussed the correctness and completeness of resolution method, and started discussing polynomiality. So next time we'll start with a small, we'll start with a small introduction to some practical things in order to hand out the programming home assignment. So the home assignment will be implementation of some of these algorithms, and we'll also discuss a bit of syntactic analysis. So your input will be a formula, and we'll discuss the implementation of parsing of syntax of formal languages using Python and well, Python Lex and Yak library. So this is what we're going to do next time, and then we'll move into Turing machines and PNP problem and stuff like that. So that's about all for today. And the practical class will be now. So thank you for your attention. I will stop the recording now. We'll do this.